This is the first time I attend one of your meetings, and I was introduced to this group about 12 years ago by John Deere, a retired USGS geologist who had a hard time living in the USGS environment because they are hostile to new ideas. So he introduced me to this, and then he talked me into writing a paper about 12 years ago on what I think pre-earthquake signals might be, because I have spent the preceding decades studying from a solid-state physics viewpoint certain properties of materials and rocks and minerals that led me to believe that many of the reported pre-earthquake signals are actually produced by a phenomenon that had been consistently overlooked, and that is linked to the generation of electricity in rocks. And when I started to understand the physics of this, I said, well, I'll go ahead and write this paper. And what I can tell you today is what I wrote 12 years ago, 11 years ago, has become 19% true. There was no basic mistake in this thing. So I want to quickly go through, and it's a very broad area, so I cannot go into many details, but earthquakes are the deadliest of all natural disasters, and the society in which we live now has about this way of dealing with the danger. They wait until an earthquake happens, then they bury the dead, clean up the mess, write new building codes, wait until the next disaster will happen. And my question was, is this all we can do? Now, there's a large community, well-funded community of seismologists out there, and they have done wonderful work. But they are doing it in a very narrow sector because they look at past earthquakes and calculate the probabilities of future earthquakes. That's something like life insurance companies are doing. They have 1 million customers, and they know exactly how many of their customers will die next month. But they will never tell you who it is who will die. So the statistics of small numbers kill the possibility of predicting. And that is the problem of the seismologists. What they are doing, seismologists are doing, they have to wait as a function of their techniques that they're using until something happens. And the magnitude 1 earthquake creates a rupture of about 1 million square feet in the Earth's crust. Only that large fracture will produce a signal that is called a magnitude 1, which is very difficult to detect. So if you go up to magnitude 8 or 9, a magnitude 9 earthquake releases energy about 2 million atomic bombs exploding simultaneously. And seismologists don't get a hint that something like this might be coming. So there's something wrong. We have to understand what happens before the earthquake rupture, and that's essentially what I did. So here you see an experiment that we did some 10 years ago here at NASA Ames with a very old hydraulic press. And what you see there is a 4 or 5 meter long granite rock. And on the far end, we have copper electrodes and 2 pistons electrically insulated from the press. And at the front, you see a copper contact. And between the two, there's just a electrometer, a picoamp meter. And when we start stressing, we immediately see, the moment we stress, there's a current flowing. And as we increase the stress, the current saturates, and then when we keep it constant, the current decays, and that goes on. We have done this experiment over 2.5 months. The current continues to decay. When we remove the stress, the current eventually goes away. What this is actually, the rocks, I have no time to go into the details, but the rock behaves like a battery, a semiconductor battery that in the moment you stress, you activate some defects in the minerals. These defects fall apart, form electron hole pairs. The electrons are tied to the volume that is being stressed, and the holes can flow out. They flow at about 200 meters per second, and they travel. We now have evidence. We know we can produce them upon command, and we see them over 100 kilometers distance as they spread out. So these are very interesting and powerful phenomena. So when rocks are stressed, they turn into a battery. And these electron hole pairs are just semiconductor physics. The electrons stay behind, the holes flow out. Well, why do they flow out, and what are they? Now here's the only equation that I want to show you, and that is a very, very simple phenomenon. Namely, in minerals, you always have an oxygen bond between, let's say, two silicon atoms or aluminum silicon atoms. And that is the structure of minerals. But due to some processes that's how I became aware of these things, that happen during the cooling from high temperatures, there are processes by which the electrons of the oxygens are given away. They are given away actually to protons, which become molecular hydrogen. And what is left behind are two oxygens, which a chemist calls a peroxy, the stuff you have in your detergent as a mild oxidant. They are sitting there as defects in minerals, and they do nothing. You can't see them until you stress them, or you heat them, or you shine UV light on them. Then they break apart. They form an electron hole pair. The electron gets trapped, sits in energy levels slightly below the edge of the valence band, and the hole is associated with the energy levels at the edge of the valence band, and that allows them to propagate through the grains, jump grain boundaries, go from rock to rock, and do a number of interesting things. So rocks turn into a battery. That's a rather fundamental discovery, and it's very strange that it took so long time. It should have discovered in the 20s. And I ran across this over a period of about almost 30 years, starting the first hint I got that this was in the late 60s and early 70s, and we published the first paper in mid-70s. And ever since, I have come back to this question, even though through my academic career back in Germany and then the last 25 years here at NASA, I have done many other things on the side. So it's a new chapter in earthquake physics, but not only in solid state, it's actually a new chapter in material science and solid state. Now here is one image that I want to show you twice. And that's essentially what is happening. You stress a rock down there, 10 kilometers below the Earth. You activate electron hole pairs. The holes flow out. They reach the surface, and at the surface they accumulate because of the dielectric constant, the difference between air and the solid. And there are many processes that happen at this interface, and we can measure all of them with a number of different techniques. Now, one technique that we are using is that we look at when these hole carriers become accumulated and reach higher number densities per area of volumes, they start to recombine. Now, it did cost energy to chase them out of bed down there 10, 20 kilometers where the earthquake is starting to happen. It takes about 2 electron volts, a little bit more, 2.4 electron volts of energy. And when they recombine, this energy is released. But it is not released, it is released on the 2 oxygens that are lucky enough or unlucky enough to participate in this recombination. So they are vibrationally highly excited at the tune of about 20 to 25,000 degrees Kelvin, and they instantly emit infrared photons as they tumble down the staircase to come back to a thermodynamic equilibrium. So we are expecting to see infrared photons emission from the surface of the rocks that we are. And this emission happens to be in the mid-infrared, where the thermal emission, those are satellites looking down on the Earth, seeing some strange increase in infrared radiation in an area where 2-3 days later there will be a big earthquake. the satellites phone it down and say, I see heat. But it's not heat, it's an infrared luminescence that had never before been described. It's depending on these quantum transitions between the vibrational excited states. Then now we can look at what do these positive holes do further. Well, they're all positively charged relative to their environment. Though they hate each other electrostatically, Coulomb repulsion will push them apart until they reach the surface and where they become trapped. But while they travel, when they hit the Earth, they will look mostly for topographic heights. Though most of these processes will happen on the mountaintops rather than in the valleys. And this we can use in the area of earthquake prediction. You have heard this earthquake in Italy, LAquila, which became famous because some seismologists stupidly assured the local people there will be no earthquake. Go home and have a glass of wine. And then 3 days or 2 days later, the earthquake hit and some 300 plus people were killed. So these seismologists are in prison right now, or at least they are sentenced to prison. There is the earthquake center, the old town of LAquila, which was so severely damaged. So this is a valley that is just dissected by 4 or 5 known seismogenic faults, which ruptured. And at the round, you see here the Gran Sasso, which is the highest mountains in peninsula of Italy. And now when you look at this, the same picture on the left, and on the right you see the infrared anomaly that is picked up by satellites. It is the mountaintops that are shining as if they were set ablaze. And that is infrared radiation that is coming from the rocks. It's not heat. It's spectroscopically different from the heat, but it occurs in the same spectral window. And actually, we are now starting a global earthquake forecasting system, which will have a satellite component where we want to develop the satellite technology to look at these things spectroscopically, not just integrate over the infrared window and say it looks like heat. No, we can see it. We can see the color of these things. Here's the same thing now. Just the talk that you gave referred to these extraterrestrials. Many of these ideas emerged because people at night sometimes see strange luminous phenomena, glows of glowing balls floating through the air, zigzagging very fast. Earthquake lights. We just published earlier this year a big paper reviewing 400 years of earthquake light, and we got it published in the core Journal of Seismology and the Seismological Research Letters, and it created quite a stir, and some of the seismologists had to scratch their head, and they said, well, can we accept this? Or so we are studying, and we have not yet reached the point where that we can reproduce it in the laboratory, but we are getting close to it. So what I want to show you is something different, namely when the number of charge carriers arriving at the surface of the Earth increases to a constant, the associated electric field at the interface between rock and air, or ground and air, becomes so high that air molecules become field ionized. So the air molecules, mostly oxygen molecules, donate an electron. They lose an electron to the ground, which goes back into the big ground of the planet, and they float away or are pushed away as positively charged air ions. And this happens over an area of, for magnitude 5, 6 earthquake, over an area of about 100 or 200 kilometers across. Happens in pulses because there are a couple processes from the transport of the charges through the Earth and these ionization processes. These are very interesting kinetic processes. They come at pulses and they form a bubble that rises through the stratosphere and then continues their way up into the ionosphere, and that's other aspects that we are studying and we want to study with the help of NASA. And if a bubble of positive ionized air rises to, let's say, 10, 15 kilometers just by ballistic expansion upward due to the electrostatic repulsion among the ions, the plasma in the ionosphere, of course, responds like a capacitor plate. The plasma is neutral, it has positive ions and lots of electrons, and the electrons are negative, and they come down about the same amount as the positive charge is drifting upwards and moving upwards through the air. And we can develop this in great detail, and we see a number of interesting phenomena. But this coming down of the electrons in the ionosphere is known as TEC, total electron content anomaly. And that's, oh, I forgot to mention one more thing. Yes, please. As the charges are building up, things on the surface of the Earth pick up this charge. So there is a paper by Tony Fraser-Smith that he published in 1978. And what he had done, and we are now repeating this, we start actually on Monday, this series of experiments. He just put 2 nails in an oak tree up here on Stanford campus and measured the microvolt signal. And the tree acts as an antenna, and it picks up all kinds of electromagnetic signals that come either from the outside, and what you see there are actually electromagnetic pulses that come from the magnetotail. When the Earth plows through the solar wind, there is in the wake, there are turbulences in the magnetic fields which collapse and produce these pulses known as PC1, PC2, PC3s. And what you see on the top there is a tree potential on the right, the signal, here plotted as frequency over time. And you see one of these PC1s. And the bottom is something that would nowadays cost $50,000 magnetometer to pick up the thing. The tree is better at picking up these signals than the $50,000. And we have $50,000 instruments at NASA, and we are going to repeat this now exactly, and we will see and whether we can learn more about by incorporating what we have learned since this paper was published in '74. Now, another thing which is of interest in to your community, you all have heard that animals can kind of feel something is coming. And we have lots of data that this is true. We are in the process of publishing some of it. Here is something that just blew me away when I first read it. I was asked to review this paper, and it's published first in a book published by a Russian author. And what had happened is in 2003, there was a big magnitude 7.6 earthquake in a sparse, relatively sparsely populated part of southern Siberia at the boundary between Russia and Mongolia. And there's a gentleman by name Alexander Shitov. He took it upon himself after the earthquake to go through everything he could put his hands on to identify what had happened before this earthquake. And he got hold of the medical records of the whole province. And the population then is only 250,000 people, not a very high statistical number, but the number of people over the long time average that came to the emergency rooms tripled during that period of time, starting about 10 days before the earthquake. Nobody knew the earthquake was coming, but people started to flock to the emergency room and said, something wrong with me. And when you look why they came, some of them had pneumonia, that's on the left in the middle. All the others that show a pre-earthquake are related to the central nervous system. Epilepsy, hypertension, and all the other phenomena that clearly point that something is working there that interferes with the functioning of the central nervous system. And so therefore, and this has actually triggered, and we got funding from NASA to study this now, and we are getting down to the point with Victor Stolz, who was here on the first day, getting down to starting to understand what is happening between ultra-low frequency electromagnetic waves and electron transfer processes in the single cells. So now I'm back to this one here. So now I want to show you the ionospheric perturbations. So when this bubble of positive air rises and the electron in the ionospheric plasma come down, this is something that is easily shown by GPS technology. Actually, the people who developed the GPS, they saw that occasionally their GPS beams are deflected and the phase shift, and they had to go at great lengths to remove this dirt. But that dirt is information on the accumulation of electrons. And what people then found over a period of about 20 years, there are hundreds of publications of this kind, is that before major earthquake, there's an accumulation of electrons at the lower edge of the ionosphere before the earthquake. And that is happening precisely about 7 to 3 days before the earthquake. And here you see an earthquake that happened. It's a good one, which I like to show, but it's already happened in 2002. It was analyzed in 2008. Alaska, magnitude 6.2. And you see on the left there is the 2D projection of the electron density relative to a normal density of the ionosphere, projected over the map of Alaska. And the things on the right and at the bottom are just vertical slices through the ionosphere in the north-south direction in this area. So so we are now starting to implement a global earthquake forecasting system at NASA Ames, and we have already strong endorsement also from NASA and the European Space Agency and the United Nations to go ahead, because the people who look at this, they say, the science makes sense. We can go ahead and try to make use of it. So now we are probably, in 3 or 5 years, we'll see that we'll get early warning, not prediction, but we can say that 2 or 3 days before, there's a tremendous increase in the chance of having a major earthquake at such and such place globally. So when I started with this, and I'm still under this pressure from my dear frenemies in the US and the seismological community, that I'm being called a fringe scientist, and I think some of you know that term. But now we start to understand the science of physics behind this, and we can say, we can start to understand. And I bring this quote from John Deere that he always adds to his email, that the Earth is stranger than we give it credit for. Thank you.
Thank you, Friedemann, for a very interesting talk. I will make one comment that, as you know, I've been monitoring a tree since 1978, and also an antenna built to Navy specifications, and the tree is better.
And Marsha will come and see me, come to NASA Ames on Monday, so we'll have a wonderful day together.
I have 2 questions. The first is, if I understood correctly, if you take that long granite beam and you press on it, you get current flow, and the current continues for as long as you're pressing. Don't you have a perpetual motion machine there?
No. You're essentially forming, if you stress a little bit, you form a kind of motorcycle battery. If you stress more, or if you stress a larger, you get a truck or a tank battery.
But you said the current keeps flowing as long as you've got the pressure on. So if it keeps flowing, your battery has infinite power, doesn't it?
Yes, because you maintain a voltage across from the stressed to the unstressed end, and it has an internal resistance, and that current flows until the battery is empty.
Okay, second question. The Earth is known to have a net negative charge near the surface, and that gives rise to the 100 volt per meter electric field. But you never mentioned that. Is it possible that somehow the electrons, or whatever it is that carries the negative charge just beneath the surface of the Earth, somehow plays a role in what you're talking about?
Interesting that you mentioned this, because believe it or not, it goes back to Benjamin Franklin, who was the first to think about the voltage difference between up and down. And at that time, as you know, the sign of the polarity of the current was not yet defined, and he called it right. He said the Earth's ground is positive, and the ionosphere is negative. However, then in the 1920s, some very famous people wrote a paper, says the Earth, no, the Earth is negative and the ionosphere is positive. And everybody copies this paper. And therefore, I talked to almost everybody in the global electric field discipline, and they all say, like you said, yes, the Earth is negative and the ionosphere. I said, how do you know? Oh, that's how we learned it. So I'm actually in the process of writing a combative paper on saying, listen, you are wrong. You misinterpreted the data. The Earth is positive and the ionosphere is negative. Because nobody has the means of these 250,000 kilovolts that exist to measure them directly. They are inferred. Then we know there is this voltage, but the polarity is actually not really directly known. Thanks, Gary. Sorry for the long answer.
Thank you for such an enlightening talk. I'm concerned about how the ionospheric heaters and the proliferation of these by not only the HARP project in Alaska, but by many countries might thwart your efforts to look at this because of the disturbances in the ionosphere being created by these technologies.
Yes, that's absolutely correct. And the ionosphere is also very heavily disturbed by any global coronal mass ejection from the sun, so geomagnetic storms. And that is why our earthquake forecast system is built on trying to collect as many indicators as we can, like the infrared emission, but if it is cloudy, you cannot see them. So we have to look at some other things. If there's a geomagnetic storm, we cannot use the ionosphere, but we may be using the animal behavior. We may use water chemistry in the groundwater or spring water. There are many there. We have about a list of 20 different parameters that we can look, and we will put them together in a decision tree, just like NASA had to do when they launched the shuttle. They have to go through A, B, C, D, check them off. If there's one thing which is wrong, doesn't matter. If it's not life-threatening, you go ahead. If it is, then you start to worry about it.
Briefly, regarding the healthcare parameters from southern Russia, it seemed to me that the 4 graphs on the left were rising fairly uniformly relatively to the other 3. So I'm wondering if we could draw a parallel between the similarity of the cause and the diseases and the commonality due to the fact that they're all rising at a similar rate, if that's indeed the case.
Yes, I'm reproducing this image or this figure from that publication without really being, I'm not in the medical field, of course, so I'm inviting people who would be interested in working with me and see. I'm in touch with this Alexander Shitov. I want to invite him to come here in December. I am organizing a small conference at NASA Ames, and I want to see whether we can establish some collaboration.
Thank you for a fascinating paper.
I'm here for the